Okay, so you see my screen, by the way. Okay. Uh, yes. So just before we get to the problems, I want to just want to define what vector spaces are and what it means, what linear dependence means. Okay. Okay. So, uh, well, okay. So, what a vector space means. So, it's a space that's sort of closed under linear operations. So let's be more precise by what we mean. And let's let's in the beginning, let's just stick to, let's say, uh R cube, let's say, which is just the space of cube, like three-dimensional space. So I have a subset S of R cube. When is this a vector space? Well, we maybe need these. We need that if X is in this set, then lambda X is in the set for any real lambda. And we also need that if X and Y are in the set, then so is the sum. And this is enough. So this is what I mean by closed under linear operation. This sort of linear, right? Uh, yeah, yeah, yeah. Okay, yeah. We just say this. This is the definition for vector space in R3. And so it sort of generalizes, but let's just stick to this. So, okay. So examples are, for example, and this is not just for R cube. I could say this for any n dimension R. Let's just stick to R to the end for now. Let's say for more general spaces. So let's stick to this. And let's look at examples and non-examples. Well, the entire vector space is definitely the entire Rn is, just to make sure if you know what Rn is, it's like n tuples of real excise real for Rn. Uh, and so okay, let me not use X here. Let's use A1, A2 up to AN. So when I say X plus Y, X itself is an n tuple and Y itself is an n tuple. So when I add them, I'm just adding the corresponding terms. And lambda times this is just multiplying lambda to each quadrant. So so the entire thing is a vector space. That's sort of trivial. I'll just leave it as is. And so is the set containing just zero. Let's also write non-examples. Okay. Uh, well, I guess we need it to be non-empty by definition. Does this include the empty? Yeah, maybe let's say it's supposed to be non-empty. And so the empty set is a non-example. I'm not sure about the empty set, but it's fine. Doesn't matter. Uh, and let's say the set containing, oh, by zero I mean the just the vector 0 0 0. This, yeah. So this is an example, but let's say we take a singleton element containing, let's say 1 0 0 0 0. This is not a vector space, right? Because the double of this is not in the set. So this is not. So can you give me more examples of vector spaces? What about a line passing through the origin? So what about the set containing lambda times, how about this set? Just lambda 0, 0 to 0, where lambda is the real. This is an example, right? So, because if I scale it up by anything, then it will be in the set this set. And if I add two elements of the set where this is lambda 1 and lambda 2, then you get lambda 1 plus lambda 2, which is also in the set. And a non-example, okay, so other than this, there are other examples. So any line through the origin through O, basically it would look like lambda times some fixed vector, right? Some fixed a1 up to an, where lambda varies through R. This is also a vector space, but if the line does not pass through the origin, then it's not an example. Why? Why is this not a vector space? Anyone?
Oh, how do you define like addition of two lines?
I'm sorry, how do you define?
Like xy belongs to like let's consider a line through O, then xy belongs to that S, and x plus y belongs to S, right? For a vector space. So how do you define the plus thing for two lines?
I don't quite understand what you mean. I mean, X and Y are not lines themselves, right? This is the, okay, so this is the set of points on the line. That's what I'm considering. So maybe let L be a line. A line in R to the N, not through O. And I'm taking the set to be a point, the set of all points P, such that P lies on L. So I mean, you don't really need to add two lines ever. So, I mean, you're just adding 2 points. I hope it's not so confusing.
Yeah, I get this, but like then how is this a vector space?
It's not, it's a non-example thing.
Oh, okay.
I want, but the line through origin is a vector space. I mean,
Yeah, that's what I asked. How is
yeah,
a
yeah.
line through origin?
Oh, you're asking me why this is a vector space?
Yes.
Oh, because just take any point P. What does it look like? It looks like lambda times a1 up to an, where
Yeah.
a1 up to n is fixed.
Yes.
Yeah. So then what does a scalar multiplied by P mean? It's just mu lambda times a1 up to an,
Yeah, which also
which
doesn't
is
mean that.
again as in this. And if I take another q, which is
Oh, right, got it.
alpha times a1 up to an, then P plus q is alpha lambda plus alpha times a1 up to an, right? Which is also in the
Yeah,
set.
yeah. Got it.
Okay. So for people who just joined, I'm just defining what the vector space is. Basically, it's a set. I'm just talking about R to the n. It's a set such that if a point is in the set, then any scalar multiple is also in the set. And if 2 points are in the set, then their sum is also in the set. So that's all it means. And it's non-empty. So notice that a line not through O cannot be a vector space, because if I take lambda to be 0 here, then it compels 0 to be in the set. So any vector space must have 0 because it's non-empty. And for that x, if you take lambda to be 0, then this condition implies that the origin must be a part of the set. So this is a non-example. Well, the zero vector does not lie in S. So that's enough for a justification. Well, and
why is that like just enough? Zero vector doesn't like.
well, because any vector space must have a zero, must have the
Oh,
zero
right.
because of this. So this does not have zero, so it cannot be a vector space.
Ah, yes.
Okay. What other examples are there? Just think about let's think about two-dimensional space, right? So we just have a plane. Looking at the plane itself, right? So the only singleton point, if the set just has one point, then the only possibility, if it has to be a vector space, is just the origin. Other than that, if we're looking at lines, then the only lines that are vector spaces are those that pass to the origin. But what other general vector spaces can you think of? What about the union of two lines? So this is a line and this is a line. That doesn't look straight, but it's fine.
Yeah, this also should be vectors.
This should
Uh,
not, right?
Yeah, this should be. Yeah.
Okay. So let's look at a specific line, right? Let's say this is the line x plus y equal to 0. This is the line y equal to x. So why is this union not, so my set is the union of x comma. So basically mod x equal to mod y, right? So why is this not a vector space?
Let's say we take -1, 1
Okay,
and 1, 1. If
Yeah.
we add them, we are expected to get in this union itself, but
right.
we
This
get
does
0,
not
2.
You're right. So the problem is that, well, on this thing, the scale, okay, so the first condition is never violated here, right? But the problem is that the second condition that gets violated, because if you take a point on this and a point on this, then their combination is somewhere over here. That's a problem. So, which is why this is a non-example. So in fact, in general, like the union of, well, okay, I'll talk about that later. So this is a non-example. Well, okay. So what can, okay, so how about we try this, that let's try this, prove that if S contains two, well, okay, if S contains three, just trying to formulate it. Okay, so I want to classify all vector spaces in R square. That's my idea here. So want to find all vector spaces in R. So how do I do that? So what do you think is the idea? So okay, here's one idea. We know that lines to origin are vector spaces. So I want to get out of this. I want to look at other sort of vector spaces that are not just lines. Now, here's my point. Suppose I have a vector space, which is not just the origin, not just the singleton element containing the origin. It has some point P, which is not the origin. Then what can you say about the set itself? Well, let's say S is a vector space. I know that. And suppose I know that P is a point different from 0 in S. Then what other elements do I necessarily know in S?
The entire line OP.
Yes, exactly. Because the first condition means that any scalar multiple of P also lies in S. So lambda P is in S for all real lambda. And if you vary lambda over reals, it would just give me this line, right? Well, it doesn't pass the origin, but fine. Yeah. Okay, but I already thought about lines, so that doesn't give me something new. So let's say S is not just the line, so it must have some other point too. Now what can we say about the set? So now what else is there in the set? So we can definitely say that this line is also in the set, right? So we know that this line is in the set. Now it doesn't pass it through. I should make the line first and then click through. But what other points are there? So now I have P, Q, and S, and P, O, Q are not collinear.
And we just saw this is not possible, right?
Well, no, but the set can have other points. This is not just the entire set. Well, right now I just said that this is true.
Oh,
But
I
there
see.
could be other points in the set, right? For example, P plus Q could be in the set.
Yeah,
So,
yeah.
So the idea is, can you show that
P plus
any
Q isn't a vector space in R square, right?
I'm sorry.
P plus Q isn't a vector space in R square, right?
Yes. If P plus Q is a vector, so what do you mean by it's not a vector space?
No, leave it. Sorry.
So, okay.
Okay, I think I got it. So like P plus Q should be in the vector space, and any multiple of P plus Q should also be like P plus Q by 2 should also be basically there.
Sure.
So now basically midpoint of,
Pranav, just go on. I'll
yeah,
just,
so like midpoint of PQ should also be there
okay.
in the plane. And by analytically we can see basically everything between P and Q will be there, right? Because
What?
midpoint of P and Q is there. Let it be like R. So like midpoint of PR will also be there.
Okay.
And then you can basically cover everything
Directly
between.
have any real
If you
combination.
just take midpoints, then you can't cover everything, right? Then you'll only cover like particular ratios.
No, you can cover basically like any real multiple, right?
Why? How?
Like lambda times P plus Q.
Yes, exactly. So the point is you can actually form R using any PNQ. I mean, like you can form any R using PNQ. And let's just look at a proof of phi. So let's say P is, P1, P2, and Q is Q1, Q2. And I want to find lambda and mu such that their sum is R1, R2, where R1, R2 is arbitrary. Just for any R1, R2, I want to show that there exists lambda and mu such that this happens. And so basically I'm just solving a system of linear equations equal to R1, and well, actually P1 and Q1 are the coefficients and lambda and mu are the unknowns. And P2 lambda plus Q2 mu is R2. And well, if you solve it, what you get lambda is equal to derivability R1 Q2 minus R2 Q1 over P1 Q2 minus P2 Q1, and mu is something like R1 P2 minus R2 Q1 over P1 Q2 minus P2 Q1. But you have to be careful here that the denominator should not be 0. But why is it not 0?
Because they're not collinear.
Exactly. So we are using the fact that these are not collinear. And so there always exists real lambda mu for any such R in R2, which means that the entire space is an R2. So basically what we've shown is that vector spaces in R square are either just 0 or line through O or the entire space. By sort of just adding elements one by one. So So this is a vector space, but then we want to expand our horizon. So we just consider another point and see what all can be inside. Well, what all needs to be inside the vector space. And then we get lines through O. And then we take another point outside this line and see what all must be there in the vector space, and we get the entire space. So these are the only possibilities. Okay. And in general, if you look at R cube, what will happen is that by similar logic, we know that this zero vector, that is the set just containing the origin, is a vector space. And now if I want another vector space in R cube, I'll pick a point P and say that, and just assume that P is in the set, and then look at and sort of close the set. What I mean by that is I put a set P, and now I sort of just keep putting elements in this set so that it is a vector space, and I just put the least number of elements possible. So that is, if I have P in the set, I only put elements that must be in the set so that I don't violate the conditions of a vector space. That is 1 or 2. So okay. So I put P in this, and then now I see what all other points must I put in the set. So if I put P in the set, I know that I must put lambda P in the set for any P. So if put P the set, then the set must at least be this much. And now I look at this set and say, okay, this is already a vector space. So I get another family of vector spaces, which is lambda P. Well, actually, let me say V instead of P, because I view these sort of as vectors. These points in space are viewed as vectors. So I'll use V here, henceforth, where lambda is here. So if you've not seen vectors before, I'm just using V for like a coordinate in the space. So it could be some A1, A2 up to AN. Here it's just three-dimensional. So the point in the space. So these are vector spaces, and note that these are exactly aligned through O. As you vary V, you'll get different lines to the origin. And now I want to expand this further. So let's just take another point outside this line, right? So I already have this vector space, but now I put another point and see what all is in the set. And now just through the previous logic, what we'll end up with is we'll end up with a plane through this line and this point. So just imagine a point. Okay, so imagine a line and a point, right? And let's say this point, okay, so if I decide to advance. So imagine there being a point somewhere in space, right? And now just think about what all, okay. So think about think about a plane passing through the line, and now rotate the plane while keeping the line. So think of this as the axis and this as a rectangle, and rotate it like a cylinder. But this plane is infinite, so it will cover everything in the space. So then there will be a point, there will be a moment where it passes through this point, right? So that's the plane that must entirely be contained. That's like the plane that must be in the set for it to be a vector space. Basically, what I'm saying is that if P and Q are non-collinear points in the space, then non-collinear with the origin, then I get this. So let me call this W. Then I get this sort of lambda V plus mu W. Lambda and mu are both in reals. I get this sort of a set. And here I'm saying that, okay, V and W are not collinear, I mean, not parallel or whatever. But actually, you can take any V and W. If V and W are parallel, then you'll actually just get this set of things. So it's fine. And you could actually check that this. So if this is W and this is V, then this set the elements of this set must be in a vector space that contain both V and W, right? But just using first and second possibilities. And you can check that this is indeed a vector space, because if you just multiply this with a scalar, you'll end up with another element of this form, right? So this is just another scalar times V plus scalar times W. And then if you add two elements of this form, then the lambdas will add and the mu's will add. So, and whenever V and W are sort of not parallel to each other, what you get is a plane through the origin. And so any plane, and so any plane through the origin is actually a vector space. And then if you take a point which is not on the plane and then make linear combinations, you'll get the entire space. So, and if you sort of extend this further, so I'm saying that you'll get R cubed. And you can show it actually. So I'm not going to show everything here, but my point is that for R to the N, we either get the origin or a line through O, which is sort of, line through O. And then we get planes through O. And then whatever the generalization of the three-dimensional generalization of a plane is. Like basically we keep adding one vectors at a time. So this sort of looks like lambda V, where lambda is real. This looks like lambda V plus mu W, where lambda mu are reals, but V, W, and the origin are not collinear. And then if you generalize that, you'll get this set. Okay, now let me just change notation because I can't keep using new letters all the time. Lambda 1, lambda 2, lambda 3 are reals. And here basically we'll get that V1, V2, V3, and the origin should not be coplanar. Because if these are collinear, then it sort of reduces to this case. Because if they're collinear, then W is just a linear comment. It's just a scalar multiple of V. And so you get the first set. And so here, if they coplanar, then you'll end up with one of these being the linear combination of the others or something of that sort, and you'll reduce to this case. And then you'll get the sum of 4 vectors, etc., till you get sum of n minus 1 vectors. N minus 1 for lambda 1, 2, lambda n minus 1 are reals, where B1, B2 up to Bn minus 1 and the origin do not lie on a well, okay, so I want to generalize this to, so just think of, so think of the, this should be not coplanar, by the way. So think of like a generalization of collinearity and then coplanarity, so on. So I let me just write the technical term, but just n minus 2 dimensional hyperplane. That's the technical term for this generalization. I'm sort of using something that I want to teach later, but just understand it spiritually. So okay, it should be this set, but exclude everything from the previous set. That's one way to put it. So basically this tier contains all these sets, but don't consider the sets that are already here, the vector spaces that are already here. I guess that's one way to put it. And then when you go further, you'll get the entire space. And so these are called zero-dimensional vector spaces. This is one-dimensional. And I'll define dimension more formally later. This is two-dimensional, three-dimensional, etc. up to n minus one-dimensional and n-dimensional. I guess this is, yeah, okay, great. So just so we sort of classified vector spaces in R to the n without details in the proof. I don't have the fine details here, but as long as there is an intuition, it's fine. So, for now. So let me define linear independence now. So this is, well, it has to do with linear algebra, not directly related to the definition of vector spaces itself, but okay. So vectors v1, v2 up to vk are said to be linearly independent. Well, let's define linearly dependent first. Linearly dependent if there exists reals lambda 1 up to lambda k, not all zero, such that lambda 1 v1 plus up to lambda k vk is 0. So what is the motivation behind this? So let's just think about a particular case where we have something like this. 3v4 equal to 0. Let's say we get something like this. So what it means is that this vector v4 is actually just a linear combination of v1 and v2. And so it's not like a new vector in some sense. Like you can use the other vectors to form this using linear combination, and hence the term dependence. And hence we call them linearly dependent, because one of the vectors can be made using the others. And if this is not the case, then we say linearly independent. So example. So if, okay, fine. So in RQ, this, so I might say that the set is linearly independent. By that, I mean the vectors and the set are linearly independent. But let's not take sets for now. So these are linearly independent. So consider them vectors in RQ. So these are linearly independent. Why? Because if I write lambda 1, lambda 2, lambda 3, and the sub is 0, then you'll just get lambda 1, 0 through this, and then lambda 2, 0, and lambda 3, 0. So these are linearly independent. How about something like 1, 3, 7 minus 1, 4, 2, and 3 minus 5. 2. Are these linearly independent? So basically we are putting lambda 1, lambda 2, lambda 3, and we want to solve that. If we can solve and get lambda 1 equal to 0 and lambda 2 0, lambda 3 0, then they are linearly independent. But if we can find other lambdas, then they're not linearly independent. So I know it's some work there. Just making your work to show whether it's independent or not. Anyone? Like, is this linearly independent or not? Or you're just too lazy to work with it?
Yeah, trying just a minute.
Okay. So if this combination is 0, then what do we get?
Lambda 1 minus 2 minus lambda 2 plus 3 lambda 3 equals 0. And then 3 lambda 1 minus 4 lambda 2 minus 5 lambda 3 0.
So let's just solve this much first. So from here we have lambda 2 is lambda 1 plus 3 lambda 3. And okay, so let me just write the other equation. And well, if I put lambda 2 here, then what does this become? So this becomes 7 lambda 1, 4 into plus 7 lambda 3, 0. This gives me lambda 1 equal to minus lambda 3. And if I put that, so lambda 2 is equal to 2 lambda 3. I think so. Is that right? Yeah. And then this just becomes 7 lambda 1. Well, I mean, minus 7 lambda 3 plus 4 lambda 3 plus 3 lambda 3 equal to 0, which is just true. Right. So this, so this and this is enough to make this true. So actually any lambda 1, lambda 2, lambda 3 that satisfies these two properties makes this true. And so if I just take lambda 1 to be lambda 3 to be well, minus 1 or maybe 1, and this to be 2, this to be minus 1, then I get 0 0 0. In fact, you can check this. So this
So
is
these are
fine.
linearly dependent, right?
Yes, so these are linearly dependent. Because one of the vectors is actually, in fact, twice of this plus this is just the first vector, right? Because of this. And so these are not linearly dependent. Okay. So now that we know linear, well, I know I promised combinatorics, but I need to cover basic linear, etc. Sorry. Okay. So okay. So now consider a vector. Okay. Wait. We have defined linear independence. I just want to make another definition, which is the span of well, set of vectors. Yes. I don't remember what the technical name is, but it's fine. So given a set S equal to vectors V1 up, well, it could be just any set of vectors. The span of a set S But intuitively, what it is it's just the smallest vector space that contains everything in S. So, for example, if I have S equal to 1, 0, 0 and 0, 1, 0, then I just want to add enough elements in this S so that it becomes a vector space. So what is that in this case? It would just be lambda comma mu comma 0, where lambda and mu are reals, right?
Yeah.
Because this is needed and this is enough, right? You'll definitely have to add these, because if I multiply this with lambda and mu, this with mu, and then add them, then that gives me this, right? And in fact, this is a vector space. This is just the xy place, by the way. And so this is the span of this set. And the formal definition is simply, it's just the linear combination of vectors where n is some natural. So note that it's a finite linear combination. So even if S has infinitely many elements, for the span, you'll only take a finite subset, any finite subset, and then make a linear combination of those. So V1 up to Vn are in the set, and lambda 1 up to lambda n are reals. And it's easy to show that this is the smallest vector space containing S. So it's, first of all, any vector space containing S must be a superset of the span of S, because these elements must be in that vector space. And then now you can show that this is indeed a vector space. So that's enough. So basically, span S is the smallest. And here by smallest, I mean any other vector space is a superset actually. So not smallest in terms of any particular metric, it's just set, subset, containing smallest vector space containing S. Great. Okay. So I have span, I have linear independence, and I have roughly this sort of classification for now. Okay, great. So now we can more formally define dimension. The dimension of a vector space is this line. Let's talk about it. Is the size of the largest independent set in linearly independent set of vectors. Yes. So basically what is going on here is that, okay, so let's go back to this example of R.
Oh, Li is the like linear independent set, right?
Yes, yes. Let me go back to slide.
So basically, for a like, if we consider a XY plane, then it will be whole R2 that I mentioned of that, right?
No, no, it won't be. So let's take that example, right? Let's take the example of the XY plane, right? Let's take XY plane in R3, right? So what does that look like? So what does that look like? It looks like lambda mu 0 for real lambda and mu. So what's the size of the largest independent set that you can take from this? So first
Like
of all,
whole
check.
R2.
But that's not linearly independent, right? Because if I take V1 to be 1, 0, 0 and V2 to be 2, 0, 0,
Oh, I see. Okay.
then these are not linearly independent because 2V1 is minus
Yeah,
V2.
yeah, So I think the answer should be 2, right?
Exactly. Yes. So first of all, we can definitely take one vector to be linearly independent, right? So we can definitely take just 1, 0, 0. But we can also take 1, 0, 0 and 0, 1, 0. These are also linearly independent, right? But can we take three vectors that are linearly independent here? So can we show that it's not possible to do so?
Yeah, because like there will be 3 equations and
So-
only 2 variables.
Uh,
If you get what I
wait.
mean.
hold on.
Okay.
Just use A. Okay. Yeah. So suppose we have three vectors such that yeah, go on.
Yeah, so there will be basically like 3 equations or 3 variables and 2 equations. You
Okay.
cannot rule out the variables from this. So yeah,
Why?
like there is an extra variable, right?
So well, I mean,
I mean,
think,
unless origin and 2 points are collinear, you cannot.
what do you mean by that? Actually, I'm not sure.
Because like then one of the point is just the scaling of the another point, right?
Even then, you won't get unique lambda.
You won't. Oh yeah, you won't because
No, I
one.
mean, you're not reducing the number of equations. I mean, you're only making the task easier if you will.
We've already shown that given two linearly independent vectors, we can achieve any point in R2.
Exactly.
So-
Exactly. That's the
Alright,
point.
yeah.
So we had already shown that if I have two vectors that are not, so if I take two vectors that are linearly independent, so okay, so if three vectors are linearly independent, then definitely any two of them are also linearly independent, right? So so if these were linearly independent, then so would these be. But I've already sort of shown in the R2 plane that if I have 2 points that are not on the same line, then I can form any other point using a linear combination of these two. And so this cannot be independent from these two. This zero is sort of redundant. So I can just focus on this. And so the answer is 2. Yes. So this dimension is 2. Although I already mentioned dimension before that it is 2, but here we now know what it means. But okay, good. And yeah, so now it's clear why the dimension of this is 0 by this definition. And the dimension of this is 1. This is 2, and this is 3. Okay. Well, I mean, we should technically show this, but I'll just skip that part.
For the zero vector,
Yeah.
why isn't the dimension 1? Because like you can have one, like 0 is
Well, the set 0 itself is actually linearly dependent because the scalar 1 times 0 gives me 0. So I have a lambda which is non-zero such that the linear combination becomes 0. So the set containing just 0 is actually linearly dependent. So if I just have a vector 0, then there is a lambda 1 which is not 0 such that this happens, right?
right, sorry,
Yeah.
yes.
Okay. But if I had a non-zero vector, then yes, the dimension would be 1. Well, I mean, it would be linearly independent. Dimension doesn't make sense. So, okay. And then I want to talk. Okay. So here's one question. Prove that. Well, okay. Rather, I want to look at it as a property rather. If the dimension It's a really nice property, by the way. Dimension of a vector space is M. M is usually like common for using for denoting dimension. And vector space S is M. And okay, then okay, let me yeah. And if S, oh not S, but if T subset of S is a set is a linearly independent set, of size less than M, then there exists a vector B in S such that T union B is linearly independent. What this means is this. So suppose I have a vector space in R to the, let's talk about smaller terms first. So let's say I have the but for plane it just becomes easy. So okay, so suppose I have R to the 7 and I'm looking at S to be a 4-dimensional subspace. But I'll use subspace for subset, which is a vector space of R to the 7. Then I know that the size of I know that the size of any linearly independent set in S is 4, or is at most 4. But it's also true that if I have a linearly independent set of a smaller size, then I can always add a vector and make its size larger. That's one interesting fact. Okay, so if I have a T, well, if I have, let's say, 3 vector, if I have one vector which is just linearly independent and hence non-zero, and it's
Oh,
not an S,
Can
then
we
I can,
consider like though let's say like there is a 3-vector space, like there are 3 linearly independent vectors in T. Then
yes,
if you see the span of those 3 vectors, that will be like 3-dimensional.
correct.
So we can always add like one more dimension.
Exactly.
because-
Exactly. Exactly. You're right. Yeah. So if I have, let's say, a subset where T has just 3 vectors and these are linearly independent, then I can always find another one S such that these 4 vectors are linearly independent. So sort of, yeah, you're right. That you can sort of look at the span of these vectors. So what is the span of T? I know that it's like a linear combination of V1, V2, V3, right? So it's some lambda 1 V1 plus lambda 2 V2 plus lambda 3 V3. The
Then
lambdas are reals.
then can't you like add vectors still like your the size of the set is like the size of the subset?
Yeah. So yeah. So the dimension of this is 3 because, well, okay. So the dimension of this is 3, and the point is that this is 4-dimensional. There must be another vector here, which is not in this. So that's the V4 that I can take. So the idea is that no matter what vector space you have, you can sort of construct that space in any order, in the sense that you can start with a vector V1 and then look at the span of V1 and then pick another vector which is not in the span. So pick V1 and then look at the span of, okay, so pick V2 in the set which is not in the span of V1. And then you can pick V3 which is in the set, but not in the span of V1, V2, etc. And you can always extend any set of linearly independent vectors which is not the whose size is less than the dimension, but by repeatedly adding vectors till its size becomes equal to M itself. So that means so what this actually means is that any Li set T such that, using short form here, such that this is less than the dimension can be extended to a set B such that to an Li set, which is linearly independent set B, such that the size of B is equal to M, which is the dimension. And now what can you say about the span of B? It must be the entire set, right? It must be the entire vector space, that is, right? So this has to be the entire vector space. If it's not, then it's definitely a subset because all the vectors lie in the set. So if it's a strict subset, then there is another element W in here. And now you can sort of put W in this and then take the span of that, and you can get an M+1 dimensional subspace, which is a subset of an M dimensional space, which is a contradiction. I mean, sort of by definition of dimension, we cannot have M+1 independent vectors in that set, right? And so basically what this means is that you can start with so this procedure ultimately ends with you getting a linearly independent set of vectors up to M, such that this is linearly independent and this spans, where the span is equal to S, means it spans the entire vector space. And this sort of a set is called a basis. So as an example, if I take the set, the set of this entire space R cube, then 1, 0, 0, 0, 1, 0, and 0, 0, 1 is a basis. Because it's linearly independent, and you can you can form a vector using linear combination of these three vectors, right? And so this is a basis, but there are other bases. For example, look at this procedure. I can just pick any such V1, V2, V3 on each step, such that each of these steps are violated. By the way, this should not be 0. Such that all these steps are satisfied, and I will always end up with a basis. So that's sort of the beauty of it. All maximal linear independent sets are bases. By maximal, I mean that you cannot add another vector to it and keep it linearly independent. So for example, if I take V1 to be, I don't know, 1, 3, 5 here, then I can take this to be anything which is not like 2, 4, 2, 6, 10 or 3, 9, 15, like not a multiple of this, right? So I could take, I don't know, 0, 1, 1, right? And then I can take any vector which is not a linear combination of these two, right? So I need to be careful. I can't just guess here. So let's take 1. Sorry, this one. 1, 1. I think this is fine. Yeah. Okay. And this is another way. And there are many bases you can make. So, so if you've seen this before, then you might also know that the determinant will be non-zero, etc. But yeah, this is just okay.
Is there any proof for the determinant thing though?
Well, I mean, I'll have to get into a lot of linear algebra then for everything to make sense. Then but there is a proof in the sense that you can induct on the size of the set and show that. But I guess induction is not very key.
Like the one I know is like too much manipulations. Like it's just. a
Well, you
little-
can manipulate the rows, etc., and get like a diagonal matrix, etc. But I mean, it's painful. But
Oh.
I mean, I mean, there is such a proof. I mean, there are proofs that do all that diagonalization. Not. I mean, what is it called?
The diagonalization is only. it's
No, no,
fine.
no, no. I don't want. Not I. It's different from diagonalization. What we're talking about.
Row
What is it?
echelon form or
Yes, yes.
something.
Row echelon form. Yeah, you're right. And yes, and I think the process is called Gaussian elimination, whatever it is. Yeah, but there are methods. You can refer to a standard linear algebra book for that. But okay, so the takeaway is that basis. So okay, so also by the way, just to make sure, these are not the only sets that span the entire set, right? I can take linearly dependent sets as well that span the entire set. Right? For example, if I have R cubed, then I could take 4 vectors which are, I don't know, 1, 0, 0, 0, 1, 0, 0, 0, 1, and then I can take V4 to be anything, right? 0, 0, 1, and V4 to be 1, 1, 1. The span of these 4 vectors is also R cubed, right? But it's not a basis because it's not linearly independent. R cubed, but this is sorry, 4, but this is not a basis because it's linearly dependent. So the point is that for any m-dimensional vector space, so if T is a set such that span of T S is equal to S, then there must be at least m vectors in T, right? Because if I have less than m vectors, then the dimension of the span of T is less than m, right? This span cannot have a dimension. Well, if this is a finite set and has cardinal, then the span of T cannot have dimension exceeding the cardinality of T. That's one thing. And on the other hand, if T is a subset, right, T is a subset of S such that T is linearly independent, then the cardinality of T is at most M. M is the dimension. And the intersection of these sets is the basis. Intersection. Set of. Well, okay. The set of bases, yeah. Okay. So we've covered certain linear independent spaces. Dimensions. Okay. So we have like a fast track idea of all this. So, well, let's look at a question that might use this. I just compiled a list of questions and need to look at the easier one. Okay. Let's try this first. So prove that. And just don't immediately tell the answer. Let ensure everyone tries. Every set of n plus 1 natural numbers whose wait. Let me reformulate it. Let B be a set of n primes, n distinct primes. and let S be a set of n+1 naturals such that uh, such that uh, such that for any S in S, the prime factors of S are in P. Prove that. Oh, before this, I also, let me just complete the question. Prove that there exists a non-empty subset such that the product of elements in T is a perfect square. Say perfect square. Yeah, before this, I should also mention that while we talked about vector spaces in R to the N, there's one more interesting, well, there are quite a few interesting vector spaces, but there's another one that I should mention. So, 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 let me just describe it. So it's the set of okay, it's this set containing vectors of the form, well, each, okay, so they're n dimensional, but each element is just 0 or 1. And the way addition works here is, and by the way, the lambda that I can choose from the definition here, well, remember the definition here allows lambda to be any real. This time lambda is only allowed to be 0 or 1. So that's the only place where lambda can come from. So lambda is 0, 1. So the scalar multiples are only 0, 1. And so this is my entire space, by the way. And how addition works is mod 2, basically. Plus V1 up to Vn. So it's addition mod 2. So A1 plus V1 mod 2, etc. And 0 multiplied by a vector is just all zeros. And 1 multiplied by vector is all ones.
If like in one of A1, A2, AN, let's say A1 is 0, then 1 multiplied by that should be 0.
Oh, sorry. Why did I write all ones? Sorry, this should be just A1, A2 up to AN. Yeah. So
Thank you
notice
for the
that
code log, by the way.
for the what?
Code log.
Sorry, I didn't quite understand.
Yeah, ignore it. No, nothing.
Is this fine?
Yeah.
Okay. So just to look at what sort of vector spaces are in this, let's look at F2, which is what, just 4 points, right? It's just 0, 0, 0, 1, 1, 0, 1, 1. Right? And what are the vector spaces in this? Can you classify them? Can you tell me all vector spaces? Well, definitely this itself is a vector space, right? And the element, the set containing just 0, 0 is the vector space.
1, 0, 0, 1.
Well, no, but it misses 0, 0, so that can't be.
What? Oh, right. I see.
I mean, the 0 vector is always in the
Yeah.
Yeah. zero
So-
element is always.
So
yeah,
basically like all 2 element set with 0, 0 in it.
you're right. Because basically I can take anything like this, right? This is in the set because notice that if you can just sort of verify it, right? So that lambda times this is either this or this, depending on what lambda you choose. And then if you add these, you get this element. So yeah, you're right. So I can also have 1, 0. I can also have 0, 1. And then if I take 3 elements, then you can show that the fourth must also be there because
We can just add the 2 non-zero ones.
yes, the sum of any 2 of these is the other one. So then this is true. So I should really write this question in the next page because I need a little more space to describe this. Let's just look at F2 cubed as well. So it's all 3 points of 3, right? So there are 8 things in it. So can you tell me all the vector spaces in this? Might be a little cumbersome. 0, 0, 0. And then 0, 0, 0 and any other element, right?
Yeah.
Along with any V which is different from 0, 0, 0 works. Right. Any of this works. So you can check that because all of this is satisfied because lambda times this is itself, lambda times V is either this or this, and then the sum of these two is V. So yeah.
Also like I think 0, 0, 0, and you take any 2 vectors which have only like 1, 1 in them. And then
Well, you can take any 2 vectors.
and then V plus W.
Yes, you're right. This also. You're right. So this again you can check. Well,
Alright, V
this
plus-
property is always true. I mean, you don't even have to check this because that is the first condition of vector space is always true for any set, right? Because you're either multiplying by 0 or 1. So if you multiply with 0, you get the 0 element. If you multiply by 1, you'll get itself. You don't even need to check that. So you only need to check sums. And for sums, you never need to check 0. So you only need to check the sums of these. And the point is that V and V plus W actually add to W. Because V plus V is 0. Because mod to everything becomes 0. That's the point. And W plus V plus W is V. So all these sort of sets also work. And then what happens if you take more sets?
So
let's-
basically, if we take like, let's say another Y, then we will get V
say U.
plus, okay, U.
And
Then-
let's say these are sort of linearly independent, right? So I can extend the definition of linear independence here as well. Just as an example, here, well, okay, here itself, for example, 1, 0, 0, 0, 1, 1, and 1, 1, 1 are not linearly independent because their sum is 0, for example. So there is a scalar 1, and scalar 1, such that their sum is 0, 0, 0. So these are linearly dependent. So let's say U, V, and W are linearly independent, right? So something like 1, 0, 0, 0, 1, 0, and 0, 0, 1. Yeah. Then
Or we can take U plus V, V plus W, and U plus W by the like previous thing of 4 sets.
and what
then-
else can you take?
Or U, V, W, U plus
Yes.
W plus W.
And you can show that these will all be distinct because of linear independence. Like for example, if this is equal to this, then you'll end up with V equal to W, which violates our assumption that I've taken linearly independent vectors. And then any
Oh, yeah.
two equal, you can just cancel out common terms and then get that you have some scalars that sum up to 0 and not all scalars being 0, which is a contradiction. But now notice that these are 8 elements. So then this must be the entire set, right? Because the entire set has 8 elements. So no matter what linearly independent UVW you take, you'll end up with the entire set. So notice that, So here again, I can talk about dimension. Here, the dimension is 2. The max number of vectors I can take such that they're linearly independent is 2. And then the dimension is here 1 here. And the dimension is 3 here. The dimension is 0 here. And there is a very interesting property about dimensions here. Notice that the size of the set is just 2 raised to the dimension. So for any S, which is a subset of F2 cubed, the dimension of S is equal, well, sorry, the size of S, vector space. Actually, V is the common thing to be used for vector space. I should just always write V is equal to 2 raised to the dimension of V. So just take a moment and look at this for some time. So just look at this and the question for some time. The question is directly related to this.
I have some idea that how this might be related to like linear algebra. And what we
Okay.
say. Shall I tell?
Yeah.
So basically, we have like n distinct primes, so we can consider like n length tuples, and like the first place is governed by P1, second is by P2, and so on
Sure.
to Pn. And then the set P is basically like for P1, the element P1 is just 1, 0, 0, everything 0 else. The for P2, the second element is like 0, 1, and everything else is 0.
Okay.
And then if we consider the elements of S, so like if there is this number, we write it as in the prime factorization. And then if the exponent is odd, we write a 1 there, and if it's even, then 0. So like you get like a F2n basically.
Yeah.
And you have that the P is the basis basically.
Yeah.
So you need a set subset S of T of S such that if you consider a product, that's basically sum of the elements in this S.
Yeah.
You need everything to be 0
The
for
sum
the
to be 0.
yeah, for it to be a perfect square.
So what does it mean for a sum to be 0 in terms of what we learned today?
So basically 0, like, oh, that should be a vector space. S should be a vector space.
No, 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 no. So
Oh, they should be
remember-
linearly dependent. Linearly
Yes.
dependent.
Yes. So we need to show that S is that set you're thinking is linearly dependent. Why is that?
Because there are n plus 1 vectors in a F2n thing.
Yes, good. So
So
here
that
is the
should be
solution.
linearly dependent.
Yes, because I mean a linearly independent set cannot have dimension more than n.
Oh, right, yeah.
Here's the idea. Let me. So
This just killed it.
exactly, this is great, right? So let's say I have this prime 2, 3 primes 2, 3, 5, 7, and I have, let's say I have an element which is 60, right? Notice that it's 2 square times 3 times 5, and I don't even really care about 2 square, right? I mean, this for all purposes to me is dead. Right? I only care about 3 times 5 because I only care about making the product a perfect square. So I only care about whether the exponent is odd or even. Right? So for any set S, well, sorry, for any element. Why is this not working? Okay, wait, fine. Give me a minute. I think it just disconnected. Okay. So for any S, which is of the form P1 raised to A1 up to Pn raised to An, where these P1 up to Pn are these P5, 7, I only care about whether the exponents are odd or even, right? So for this, I consider a corresponding tuple, which is A1 mod 2, so on up to An mod 2. And now, okay, so if this is S1, let me write this as A11 up to A1n. And so if I take the product of like S1, S2 up to Sk, what does it correspond to as a tuple? Like the exponent of P1 would simply be A11 plus A121, etc. up to A. So make it clear that I think right here. Up to AK1, right? So then this would consider to would correspond to something like this. Right? It would exactly correspond to this actually. So this is K1 mod 2, so on up to A1n plus so on up to AKN mod 2. And so that's the motivation behind considering the set F2n. Basically, for any S, consider its corresponding element in F2n, which is where the ith place is 1 if the exponent of the ith prime is odd, and is 0 if the exponent of the ith prime is even. Right. So I have a corresponding element. So I have like a correspondence from S to a subset of F2n. Okay. And what does it mean for me to show that there is a non-empty subset of S such that their product? I'll just read chat. Subsets of S. So there's a non-empty subset of S whose product is a perfect square. It corresponds to saying that. Well, also, so basically now the problem is reduced to this. Let S be a subset of F2n such that cardinality of S is n plus 1, and there might be repetitions. So I'm okay with repetitions. Okay. Repetitions. Prove that there exists a non-empty subset of S such that the sum of elements in T is 0. But that's exactly the same as showing that S is linearly dependent because the only scalars allowed in F2n are 0 and 1. So in the definition of linear independence, so where was it? If the only scalars allowed are 0 and 1, then this is basically a subset of the vectors that act to 0, right? Because I'll only take those vectors that have a 1 with them, and the ones with 0 are just irrelevant. Right? So, which is why this is just, so basically the problem is prove that an n plus 1 element subset of F2n is linearly dependent. But that's true because the dimension of this is n. But this is true because the size of S is more than the dimension of the entire vector space. And that is the proof. And notice that this is tight, by the way, because if S is replaced by N, then I can just take S to be the set of primes. So that's definitely no product. Well, that kills the problem. So
Is there a non-linear algebra solution?
I guess probably, well, let me put.
Maybe induction on the number of primes.
Well, I guess you can do this. Oh, well, induction could work, but you could do this if there's no product that's a perfect square, then I think you can show that. Well, I mean, it could be something like this. Basically, you can show that for any two distinct subsets, S1 and S2, consider the product of elements of, I mean, for any two distinct subsets T1 and T2 of S, consider the product of elements in T1 and the product of elements in T2, then the exponents would differ somewhere in parity. Because well, okay, so what I'm trying to say
I think that would be a linear algebra thing, but just hidden.
kind of kind of, yes, it is kind of basically then I'll prove that if I have those exponents, then all 2 to the n plus 1 different products should correspond to different parities of exponents, but there are only 2 to the n possibilities, which is the contradiction.
Yeah,
That's
okay.
yeah. But maybe there's some induction. I mean, I guess there could be. Yeah, I'll have to think of it. Yeah, I'm not sure. I mean, I guess anything that I'm trying to prove ends up with looking at the exponents mod 2, which is in some way related to this. Yeah. But I'll try to think about it. Let's just do one more problem and then we'll end the session today, and we'll just take it again. We'll pick it up from the day after tomorrow. Let's do. Okay, so here's problem. So I have a simple graph G with n vertices and m edges, and m is at least n plus 1. Each edge is red or blue. So here's what we can do. We can repeatedly apply the following equation. Choose a vertex and change color of each edge incident on it. Prove that there exists a coloring, but there exists an initial coloring. Such that it is impossible to make All letters the same color. But G is given, by the way, so you cannot choose G. You can only choose the coloring. Wait, let me just check. This is right. Yeah. I will have to end the class in 5 minutes. We can take this question the next time or do it offline as well.
So by the way, I have some idea.
Yeah.
So basically we can try to make like instead of m edges, we can do it for like n choose 2 edges.
Okay.
And then remove some of the edges because like all the edges work independently. One edge is not dependent on another edge, right? Whenever we make a move.
What do you mean? We pick a vertex and then switch everything that is incident on P.
Yeah, but so like whatever operation we do, it's like vertex dependent. Like so basically, suppose we have to switch the color of one edge, we'll pick like some vertex adjacent to like some vertex which lies on that edge, right? One of the two vertices.
But it's possible for you to make smaller number of edges monochromatic, but maybe not the entire complete graph, right? I mean, if there's just one edge, then you can definitely make it monochromatic.
Yeah, so basically the idea is, suppose out of these n edges, we have like a set of n out of these n choose 2 edges, we have say a set of m edges such that m minus one of them are red and one is blue, or like some less number is red and other is blue.
Okay.
And then we remove all the other edges except those m edges.
Okay.
And then we can't make it like monochromatic again, right?
Why?
Invariance maybe?
So you're saying that if you color one edge different from the others, then you can't make it monochromatic? And that's what you're saying.
No, I don't mean that actually.
But-
And okay, I think it doesn't work what I was saying.
I mean, what is the point of adding the other edges if they don't even matter?
So the point of adding other edges is because like if we have to work in like say F2, then if you have like all the edges, we can consider the tuples for like what do you say this? Vertex 1, you can consider like 1 if the edge is red between 1 2, vertex 1 and 2, and 0 if it's like blue. And similarly for
I
1.
see, but then might as well just consider the vector space only on the edges that are in the set, right? I mean,
How do you
instead of
consider that? Like I was thinking of such a vector space, but that-
just m dimensional, right? The ith place talks about the ith edge.
oh,
You can do that. That's what you're doing basically, because you're just taking sort of E1, 2, E1, 3 up to E1n, and then E2, 3, E2, 4 up to E2n, etc. And then you're just dropping the edges that don't matter.
yeah,
So then you've shrunk it to basically m edges, right?
yeah.
So might as well just consider the space containing those m edges.
Oh. But how do you like what is the size of each element in that vector space?
I mean, it's basically just f2m. That's it. It's just m tuples, right? If it's red, it's a 0. I mean, if my graph is this, for example,
Oh, so basically
so
what we
this
do
is
is
E1, E2, E3, E4, E5, right? So if E1 is red, then put a 0 here. E2 is blue, put a 1 here.
oh I see. And then we can consider like the set of like if you are considering a vector space, like not a vector space, like a set where everything is like convertible to each other. So like we have some initial value, and then we say we do one move, we get another 5 tuple, and then
Yes,
that's also
exactly. And basically, you want to show that there is some initial configuration where you end up with neither this nor this. Right?
Yeah. So we have to show that it's linearly independent.
Well, I don't know what you need to show. I just gave the hint for the space.
Okay.
You can considering f2m, where each position in the vector corresponds to an edge, and then red is 0, blue is 1, whatever. Whatever. So that's how it's working. And what is this operation doing? Think about that. It's like adding something. So, say adding a vector.
Yeah. So basically, if you consider some like so it's adding a vector where it's 1 if that edge is passing through that edge, passing through that vertex, and 0 otherwise.
Yes. So you have some set of vectors. So just
Yeah,
think
right.
about that. Okay. So then I guess you could put up solutions on Discord, but I'll put the solution to this later, and then the next class we'll do more problems that use data. Okay. Cool.
Shall I
Question?
put up the screenshot of the question?
Yeah, sure.
Can you share this PDF?
Yeah, I'll share it.
Thank you.
Yeah, no problem.
Shall I stop recording now?
Yes. I'll also try to make a LaTeX document that describes dimension, linear independence, everything in detail, and proves more things.